Hello everyone. In this lecture series, we are going to discuss about one more important aspect of airport, that is design of taxiway or taxiway design. So in general, if I want to give an introduction to taxiway or design of taxiway, the main function of taxiway is to provide access from the runway to the terminal area and service hangars. It is evident that the speed of aircraft on the taxiway will be much less than that of the runway at the time of landing or takeoff. The standards for the taxiway design and construction will therefore not be as rigorous as that of the runway. An apron taxiway is a taxiway located as usually on the periphery of an apron. The term dual parallel taxiway refers to two taxiways parallel to each other on which aeroplane can taxi in the opposite directions. A terminal taxi line is a taxiway on an apron used for the access to the gate positions. In this chapter, the salient features associated with the taxiway design will now be briefly described. So if we can see the slide, the background of the slide just indicates the taxiway. You can see a single taxiway or a parallel taxiway where the aircrafts are taxied in opposite directions or somewhat in a parallel to each other. So moving on, we are going to now discuss about the factors that are governing the designing of a taxiway. The following factors or considerations govern the layout of the taxiway. First one, the arrangement. The arrangement of taxiway should be such that the aircraft which has just landed does not interfere with the aircraft taxiing to the takeoff. Next, the second point is busy airports. It is desirable to locate the taxiway at various points along the runway on busy airports. It will then be possible for landing aircraft to leave the runway as early as possible for making it clear for use by other aircraft. Such taxiways are known as exit taxiways or turnoffs. For busy airports, where taxiing traffic is expected to move in both directions simultaneously, parallel one-way taxiways should be provided. Next, moving on to our next point, that is crossing. As far as possible, the crossing or intersection of the taxiway and active runway should be avoided. The next point, higher turnoff speed. If exit taxiways are designed for higher turnoff speeds, the runway occupancy of the landing aircraft is reduced. It will thus result in the increase of the airport capacity. Next, the fifth point, the route. The selection of the route of taxiway should be made in such a way that it results in shorter practicable distance from the terminal area to the end of the runway used for the takeoff. These are some of the factors which govern the selection of taxiway. Let us move on to next, geometric design or geometric standards of taxiway. The geometric standards for taxiway. The following 8 elements of the geometric standards of taxiway will be discussed. The first one, length of taxiway. The length of taxiway depends upon the distance between the apron and entry end or exit end of the runway. The limiting length of taxiway is not recommended by any organization, but to save fuel consumption, it should be as short as practicable. Next, second point, longitudinal gradient. If the longitudinal gradient is steep, there will be more consumption of fuel. The maximum longitudinal gradients recommended by the ICAO are as follows. For A and B type of airports, it is 1.5%. For C, D and E type of aprons, 3%. See, this ABC are we have already discussed about this ABC type of airports in the different types of classification of airports in the previous discussions. Next, we will move on to our third point, that is rate of change of longitudinal gradient. The available sight distance on the pavement is affected by the rate of change of longitudinal gradient. The maximum rates of change of slope for 30-meter length of vertical curve are recommended by the ICAO as follows. For A, B and C type of airports, it is 1%. For D and E type of airports, it is 1.2%. Let us move on to our next point, that is the sight distance. The sight distance is one of the factors that is governing the geometric standards of taxiway. The speed of the aircraft on the taxiway is lower than its speed on the runway. Hence, the smaller values of sight distance will be sufficient on the taxiway. With respect to sight distance, the recommendations of ICAO are as follows. First one, for A and B type of airports, the surface of the taxiway should be seen for a distance of 195 meters for a point 2.10 meters above the taxiway. Second point, for C, D and E type of airports, the comparable dimensions are 300 meters and 3 meters. The FAA does not specify sight distance for the taxiway. Next, fifth point, the transverse gradient. For the quick disposal of the surface water, it is necessary to provide the transverse gradient for the taxiway. The ICAO recommends the following maximum transverse gradients. For A, B and C types of airports, it is 1.5%, and for D and E type of airports, it is 2%. The minimum transverse gradient is not specified, but it will be desirable to provide at least 0.5% of the transverse gradient. The ICAO does not specify any value for the transverse gradient of taxiway shoulders. The FAA, however, suggests that it should be 5% for the first 3 meter width and 2% thereafter for all types of airport. Next, we will move on to our next point, that is the turning radius. A horizontal curve is to be provided whenever there is a change in the direction of the taxiway. It is necessary to design the curve in such a way that the aircraft can negotiate it without significantly reducing the speed. For this purpose, the circular curve of larger radius is more suitable, and its radius can be obtained from the following formula. R is equal to V square divided by 125. You can see the formula on the screen here. Next, where R is equal to radius of the curve in meters and V is equal to speed of aircraft in kilometers per hour, and F is equal to coefficient of friction between the tire and the pavement surface. Usually it is assumed to be as 0.13 meters. We will move on to our next point, that is width of the safety area. Width of safety area. The safety area of the taxiway is made up of partially paved shoulders on the either sides plus the area which is graded and drained. It may expected up to a point where it intersects a parallel runway, taxiway or apron. Before the advent of jet aircraft, the shoulders were given either of the following two treatments. The first one, the natural ground protected with the low growing vegetations, or it is stabilized granular material coating where the soil or climatic conditions do not permit easy maintenance of plantation. With the arrival of jet aircraft, it became necessary to protect the shoulders from the soil erosion due to high speed of the jet exhaust. It is therefore suggested that the minimum width of 7.5 meters of shoulders adjacent to the pavement edge should be paved with a light strength material with the following particulars. The first one, the shoulders must be thick enough to support the airport patrol vehicles and the sweeping equipment. The shoulders should normally be treated with a bitumen. The surface should be made of such materials that disintegrations due to the hot blast of the jet engine does not occur. The surface should be smooth and impervious. The eighth point is width of the pavement or width of the taxiway. The width of the taxiway is much less than the runway because of the following two factors. The first one, the aircrafts are not airborne of the taxiways. The second point is the speed of the aircraft on the taxiways is far less as compared to that on the runways, and hence it is possible for the pilot to maneuver easily on the small width of the taxiway than on the runway. The taxiway width recommended by ICAO are as follows. For A and B type of airports, it is 22.5 meters. For C type of airport, it is 15 meters, and for D type of airport, it is 9.9 meters. For E type of airport, it is 7.5 meters. The following figure shows. I have made a figure. I made a figure available in this slide. The figure shows the typical cross section of a taxiway for the airport of A and B type. You can see the various measurements of different A and B type of taxiways in the figure itself. So let us move on to our next topic, that is functions of exit taxiway. What are the functions? The functions of exit taxiways is to minimize the runway occupancy by the landing aircraft. The location of exit taxiways depends on the following factors. First one, the air traffic control. The rapidity and the manner in which the air traffic control can process arrivals is an extremely important factor in establishing the location of the exit taxiways. The second point is exit speed. The aircraft will require certain length of runway to bring down its landing speed to the turn-off speed. The maximum speed with which an aircraft can turn and enter the exit taxiway is governed by the type of aircraft. The value of exit speed will decide the location of exit taxiway. The third point is location of runways. The location of runways the location of the exit taxiways is also influenced by the location of the runways relative to the terminal area. The fourth point is number of exits. The number of exit taxiways to be provided will decide their location. For instance, if only 2 exit taxiways are to be provided, they would naturally be placed at the ends of the runway. If there are more number of exit taxiways, they will be suitably spaced along the length of runway. The fifth point is pilot variability. The rules for flying transport are relatively precise, but even there are a certain amount of variability among pilots is bound to occur, especially in respect to the braking force applied on the runway and the distance from runway threshold to touchdown. The sixth point is topographical features. The topographical features. These include high altitude, deep valley, obstructions in approach and turning zones, etc. They have also some impact on the location of the exit taxiways. The seventh point is type of aircraft. The landing speeds for various aircrafts are different, and accordingly the distance required to reduce the speed to the exit speed level will also vary. The type of aircraft likely to use the runway should therefore be studied. The eighth point is weather conditions. The time required by the aircraft to slow down to slow down to the exit speed is influenced by the factors like wind, temperature, etc. These are some of the functions of the exit taxiways. Let us move on to our next concept, that is design of exit taxiway. Design of exit taxiways. What are the conditions that we are going to discuss here? The following are the principles governing the designing of the exit taxiway, connecting the runway and parallel taxiway. The first one, angle of turn. The total angle of turn of 30 degree to 45 degree can be negotiated in a satisfactory manner. The smaller angles are preferable because the length of the curved path is reduced. The sight distance is improved and less concentration is required on the path of the on the part of the pilots. The right angle or 90-degree exit taxiways, although not desirable from the consideration of minimizing the runway occupancy, are sometimes constructed for other reasons. The second point is the compound curve. It is necessary to provide a compound curve for high turnoff speeds of about 65 to 95 kmph. It minimizes the tire pressure on the nose gear and is relatively easier to establish it in the field. Its shape is similar to that of a spiral as shown in the figure. I have made a figure available in the slide as shown in the figure 5.5. The main curve of radius R2 should be preceded by a large curve of radius R1. The values of R1 found experimentally suitable for different speeds are as follows: 65 kmph for 65 kmph 517 meters, 80 kmph 731 meters, 95 kmph 941 meters. So in this figure, R1 refers to the radius of entrance curve. Here you can see here, this is the entrance curve. The radius of this entrance curve is R1. The radius of the central curve is denoted by R2. L1 is equal to length of the entrance curve. L2 is equal to length of the central curve. Hope you have understood this concept. Let us move on to our next point, that is exit speed. The most significant factor affecting the turning radius is the exit speed of the aircraft and not the total angle of turn nor the passenger comfort. The fourth point is lengths L1 and L2. The values of L1 and L2, that is length of entrance curves, can be obtained by using the following equation. L1 is equal to V cube divided by 45.5 CR2. L2 is equal to pi into R2 D2 by 180. The value of constant C is 0.39 and D2 is the deflection angle of the central curve. Occupancy time. That occupancy time of an aircraft therefore entering the taxiway from the runway is composed of the following four components. First one, time required for the flight from the threshold to the touchdown of the main gear. The second point is the time required for the nose gear to make contact with the pavement after the main gear has made contact. It is about 3 seconds. The time required to reach exit velocity from the time the nose gear has made contact with the pavement and the brakes have been applied. The time required for the aircraft to turn off to the taxiway and clear the runway. It is about 10 seconds. The sixth point is shape of a taxiway. A slightly widened entrance of 30 meters, gradually tapering to the normal width of taxiway is preferred. The widened entrance gives more latitude to the pilot in using the exit taxiway. The seventh point is the stopping distance. It is necessary to provide the sufficient distance to comfortably decelerate an aircraft after it leaves the runway. This distance is measured from the edge of the runway pavement along the exit taxiway, and it is known as the stopping distance. The equation used to find out the stopping distance is as follows. The stopping distance is equal to v square divided by 25.50 d. The average declaration rate d is usually taken as 1 meters per second square. The turning radius. The turning radius for smooth and comfortable turn is calculated by equation mentioned earlier, namely r is equal to v square divided by 125 into f. This is how we are going to calculate the turning radius. So let us move on directly to the problem. The problem is nothing but the design of you are given an airport taxiway to be designed. It is simple as that. So we have looked upon some of the procedures, or we have looked upon the procedure how to design a taxiway in the previous slides. So in this slide we are going to look upon, you have been given a problem to design a exit taxiway. In this case I will read out a problem. Design an exit runway joining a runway and a parallel main taxiway. The total angle of turn is 35 degree and the maximum turn-off speed is 80 kmph. Assume the following. Radius of entrance curve is equal to, entrance curve means radius of entrance curve is r1. r1 is equal to 731 meters. Runway width is equal to 45 meters. The width of the runway is 45 meters and the taxiway width is given as 22.5 meters. Suggest the maximum separation clearance and draw a neat sketch showing all the design elements. So this is a very important problem from your examination point of view. So what we have to consider is, whatever the factors we have discussed in the previous slides, we have to consider all the factors and we have to design the exit taxiway. First factor is radius of the central curve. We have to determine the radius of central curve. The radius of entrance curve is given as 731 meters. So we have to determine the radius of the second or the R2, that is central radius of the central curve. R2 is equal to v square divided by 125 f, which is equal to v square is equal to velocity. V is equal to 80 kmph. It has been given as, and the maximum turn-off speed is given as 80 kmph, that is v is equal to 80, and f is the constant, that is 0.13. We are going to get a value of about 394 meters. Length of, that is R2 is equal to 394 meters. Radius of the central curve is equal to 394 meters. Length of the entrance curve, that is L1. Length of entrance curve L1 is equal to V cube divided by 45.5 CR2, which is equal to 80 cube divided by 45.5, and C is a constant which we have already discussed, that is C is equal to 0.30 into R2. R2 we have calculated here 394. We are going to substitute the value of R2 here. So we are going to get a length of entrance curve as 73.23 meters. Deflection angle of the entrance curve. So what we have to determine here, deflection angle. So deflection angle is given by D1 is equal to 180 L1 divided by pi into R2. So if you want to know about deflection angle, so deflection angle is given by this formula. Substitute the value of L1 and substitute the value of R2, which we have calculated in the above cases. We are going to get the value as 5.75 degree. Next, deflection angle of the central curve. We have to determine the deflection angle of an entrance curve and the deflection angle of a central curve. The deflection angle of a central curve is given by d2 is equal to 35 degree minus 5.45 degree 45 minutes, which is equal to 29 degree 15 minutes. So length of the central curve L2, the length of the central curve L2 is equal to pi into R2 into D2 divided by 180, which we are going to get the value as 201.14 meters. The stopping side distance or stopping distance SD is equal to V square divided by 25.50 D, which is equal to, substitute the values of T, and we are going to get 250.98 approximated to 251. The distance is to be measured from the edge of the runway pavement along the center line of the exit taxiway. We have two more cases, that is seventh point is for a major airport installation with an instrumental landing facilities, the separation clearance as specified by ICAO, it is taken as 184 plus 22.5 plus 11.25. Therefore, available length of taxiway is equal to 217.75 divided by sine of 35 degree. So you are going to get a length of the taxiway as 320.79. It should now be checked that this distance is at least equal to the side distance as calculated above. It becomes sometimes necessary to increase the separation clearance to accommodate the stopping distance within the length of the exit taxiway. The fillets of the radii 22.50 meters and 60 meters are provided. You can see the fillets. Provided respectively for 35 degree and 145 degree changes in the directions. This is how you can draw the diagram of the exit taxiway for the purpose of taking the deviation from parallel track, that is runway to taxiway. Hope you have understood this problem. Thank you.